Okay guys, I think this is gonna be the last video in Unit 5. We will cover the age of the universe and the eventual fate of the universe, okay? So let's start with the age of the universe. By the way, I'm using GoodNotes for this, and for these notes I mean. And I've seen that in Notes, which is another app for an iPad, they have a feature that kind of like makes your handwriting look prettier. So hopefully this will be introduced in GoodNotes as well, but maybe I will switch to another app. We will see. Anyway, so to talk about the age of the universe, we have to first talk about the Doppler shift, okay? The Doppler shift is a concept that applies to waves in general. And let's go see a very simple example of the Doppler shift for a moving ambulance, okay? So let's pretend that this is an ambulance. Okay, very simple sketch. Moving with some velocity v towards us. And let's assume that here I am, standing at some distance from this ambulance, and I'm stationary, and the ambulance moves towards me. Then what's gonna happen if the sound waves have some lambda, some wavelength? Initially they will be like this, right? If v is 0, then the wave fronts will look like this, and they will have a constant lambda. Okay, so this is gonna be lambda, this is gonna be lambda, this is gonna be lambda, and so on. But if the ambulance is moving, let's erase this and let's see what's gonna happen. Oops. Okay, so let's delete this. And now let's say that v is larger than 0 and it moves towards me. Then the wave fronts will get compressed, if you will, meaning that lambda will shrink. So the wave fronts will look like this. So something like this. As it moves towards us, you see how this lambda shrinks, okay? I hope this makes sense. And because it shrinks, we hear a louder noise as the ambulance approaches us, right? So let's write that down. Lambda shrinks when the vehicle moves towards us. Let's move over here. Therefore, we hear a louder noise. But if I am standing over here, okay, something like that, and the ambulance now recedes, meaning that it moves away from me, okay, then the lambda that I'm gonna hear, actually, no, not this way, sorry, let's draw again, okay, lambda will get wider, okay, therefore, so lambda widens. So let's write this down as well. When the ambulance moves away from us, lambda widens. Therefore, we hear a softer noise. And when I say softer, I mean less loud, if that makes sense. And the bottom line is that if the vehicle moves towards us, then we hear a louder noise. So lambda is louder, so the noise is louder than what the sound would be if the ambulance was stationary and we were stationary as well. Okay, and if it moves away from us, then we hear a softer or less loud noise compared to what the noise should be if the vehicle was stationary. I hope this makes sense. This is a Doppler shift. You can, if you stand out in the street when an ambulance is passing, you can actually experience the Doppler shift. Okay, now what does that have to do with us and the discussion about stars and space and so on? It turns out that, as I said in the beginning, this phenomenon applies to any kind of wave. Okay, so the same phenomenon applies to light. Okay, so if we have some spectrum that we received from some star, okay, and maybe we have some lines, some emission lines, say, okay, assume we have emission lines. Actually, we usually have absorption lines, but anyway, let's pretend it's emission lines. Okay, so we have the red and the blue, right? And maybe we have yellow somewhere here in between. Okay, then if we receive the spectrum, okay, so maybe this is the spectrum of light here in the lab. Okay, so this is what you observe from hydrogen emission lines, for example, here in your laboratory here on Earth. Okay, then what's going to happen if the star is moving away from us is what is called the redshift. So the red will move down here, the yellow will move down here, and the blue will move down here. So you see how we have a shift towards the red, as they say. That's why it's called redshifted. So this is the spectrum. So this is the spectrum in the lab, and this is the spectrum for a star moving away from us. All right, so since it's moving away, it's redshifted, meaning that just like in the case of the sound, if it moves away from us, we hear a less loud sound. So if a star is moving away from us, we see the blue light shifting towards the red, or otherwise towards longer wavelengths. Okay, because in the case of the sound, we have a longer wavelength, therefore we hear a softer sound. Okay, hope this makes sense. Let's go see this website. I cannot just email anyone. I use their website and ask for permission, but this is from the West Texas A&M University and Christopher Bert or something like that, Dr. Christopher Bert. Okay, this is for educational purposes, so let's go see this picture. So in the middle, you see what the spectrum looks like if it's stationary. In the bottom, you see the blue shift, which we didn't mention. So if the star is actually moving towards us, light, these absorption lines, they are going to move towards the blue, towards shorter wavelengths, okay? Whereas for the redshifted case, that's a star that moves away from us. Therefore, all absorption lines move towards the red, okay? Towards longer wavelengths. So, what do we care about this? Why does it matter? It turns out that, let's create a new page. So, redshift or blue. Actually, let's just stick to the red for now. So redshift implies that a star or a galaxy moves away from us. It turns out that most galaxies move away from us which is something that you probably heard in kindergarten as the expansion of the universe. And this is something that was established about 30 years ago, I think, with the work of a group in Australia, if I'm not mistaken. And one of those people was a professor in the university where I got my PhD from. But I might include that in the description. Okay, so let's move on. Let's quantify the shift in wavelength. Okay, the shift, in lambda as this parameter, this variable z, which is given by the difference between the wavelength we observe in the lab and the wavelength we observe from the star that moves either towards us or away from us. Okay, so delta lambda over the lambda in the lab. Okay, so this is a dimensionless quantity since we are dividing meters with meters, right? So this is dimensionless, and this is also equal to the shift in frequency over the frequency in the lab, and this is also equal to the velocity of the moving object over the speed of light. Okay, so the velocity of the moving object is called the recession speed. Okay, recession speed, and lambda and f in denominator are the ones measured in the lab. So let's do an example. So the wavelength in the lab is let's say 658.285 nanometers, and the wavelength of the absorption line as measured from a star, as we get it from a star, is 656.315 nanometers. Okay, so since, okay, the first observation when you are dealing with these problems, okay, we talked about delta lambda here, but we didn't specify which do we put first, the lambda of the star or the lambda in the lab. So let's go talk about that. So since here the lambda of the star is larger than the lambda in the lab, okay, the star moves away from us. Okay, so delta lambda over lambda would be equal to v over c. Therefore, the speed of the star is going to be c times delta lambda over the lambda in the lab. Okay, and we actually use lambda star first. So lambda star minus lambda lab over lambda lab. Okay, and if we plug in, delta lambda is just 0.03 nanometers. Okay, so times 10 to the negative 9 meters. The lambda in the lab is 656.285 times 10 to the negative 9 meters. So meters cancel, 10 to the minus 9 cancels. And then times the speed of light, times 3 times 10 to the 8 meters per second. And this gives us 13,716.6 meters per second. Okay, and let's put a note over here. So note, if the wavelength of this absorption line we receive from a star is less than the same line as we observe it in the lab, then we have blueshift. V will be negative in the sense that this moves away from us. Okay, so the velocity is going to be negative in the sense that this body, it can be galaxy, it can be a star, moves away from us. Okay, so remember when we said in the beginning of this series about topic 11 beyond space that almost everything and anything we know about the stars comes from light that comes from these stars. So this Doppler shift phenomenon that we observe from spectra is related to light, right? So a very, very important discovery about 100 years ago came from Hubble. So Hubble's law. This is a very famous astronomer, okay? And very cool looking. I mean, if you, let's go find. So Hubble, oops. Edward, I think it was his name. Edwin, sorry, Hubble. So there he is smoking his pipe. So don't smoke, guys, but okay, this guy looked cool to me. So Hubble's law, if we plot, so plotting, oops. So what did this guy do? So plotting the recession speed, so V, versus the distance of a galaxy yields a straight line. So this was a very important discovery in astronomy, perhaps the most important, okay? So the Doppler shift allowed astronomers to measure the speed of galaxies and objects in the universe. And then the techniques that we mentioned in the previous video, remember when we talked about Leavitt and her work on determining the speed of Cephiads, sorry, the distance of Cephiads and so on. Then this allowed Hubble to just come and collect as many data as he could find, I guess, and plot the velocity, so the recession speed, okay, versus the distance, okay? And he found something like this. So let's use red to put various dots. Okay, so he found this straight line, okay? So a simple proportionality law was uncovered, okay? And since this is a straight line, it has a slope, right? A constant slope, okay, that we can calculate. And this slope is called h0, okay? So V is related to distance with this multiplication factor h0, okay? Now h0 was, which is called the Hubble's constant, okay? h0 is equal to 7.9 kilometers per second per megaparsec, okay? This is how it's defined. And it's called the Hubble's constant. And it's not actually a constant in the sense that every few years more data become available, so this thing is recalculated and reestablished, so it changes, okay? If we want to turn this constant into SI units, so let me show you something. So we have 70.9 kilometers, so we have to multiply by 1000 meters, right? And then seconds are remain as they are, and then we have megaparsecs in the denominator, and 1 megaparsec is 1 parsec is 3.1 times 10 to the 6 meters, And then since we are dealing with megaparsecs, we also need the another 10 to the 6 for the mega. So actually meters cancel. And this Hubble constant is also equal to 2.29 times 10 to the negative 18 seconds to the minus 1, okay? This is not hertz, okay? It's just inverse seconds, okay? All right, so Hubble makes this plot, finds the proportionality constant. Let's see what we can do with it. Let's see some implications. So age of the universe. So since speed is distance per time, right? Then v naught is some distance d naught over t naught. Therefore, the plot implies that everything started from a point. Okay, because the light is strained pretty much. Okay, now v naught over d naught, okay, is equal to 1 over t naught. Therefore, the slope, what I call v naught and d naught and t naught here are just constants. Okay, so 1 over t naught is the inverse life of the universe, right? So v naught over d naught. So if we go back to this plot, we can think of no, actually you don't have to look at the plot. So v naught over d naught is 1 over t naught. Therefore, the Hubble constant is equal to 1 over t naught over the life of the universe. So t naught is 1 over h naught and is equal to the life of the universe. I hope this makes sense. Okay, so the inverse of the slope is simply the life of the universe, just because everything started from the same point, which you can see from here, that distance is, velocity is distance per time, okay? So T naught, the life of the universe, is 1 over 2.29 times 10 to the negative 18 seconds to the minus 1, which becomes seconds because it goes in the numerator. So this is 4.37 times 10 to the 17 seconds, which is 13.85 billion years for the age of the universe. It's actually a little bit higher than that. And I'm gonna write that down. So Hubble's constant is not really a constant. As it depends on observational data. In general, the age of the universe has been calculated to be between 10 to 20 billion years, depending on h naught. All right. Now let's go talk about the fate of the universe. So we already established that the universe is expanding. Whether it will keep expanding or stop expanding, or start shrinking depends on how much mass there is in the universe. Or equivalently, on how much density the universe has. So the accepted density of the universe at this point is the accepted, the amount of mass is important because that tells you how much gravity works, like how much gravity there is in the universe. Okay, so the accepted density is, let's put it here, rho. It's about 9.9 times 10 to the minus 30 grams per cubic centimeter, which is really like, or about 6 protons per cubic meter. That's nothing, like 6 protons per cubic meter. So the universe is kind of empty. Okay, this is what this density tells you. Then you might object and say, but celestial objects have a density like the Earth has about, I think, 5 grams per cubic centimeter, and then you have stars, etc. Yes, that's true, but then the universe is mostly empty space, right? So because we account for that when we calculate this density, then the density is really small. Okay, so the critical density which is determined theoretically is also rho equal to about rho critical. So let's put that subscript. It's about 9.9 times 10 to the negative 30 grams per cubic centimeter. But what's so important about the critical density? If rho is about equal to rho critical, the universe is flat, meaning that there is no expansion or contraction. If the density of the universe is larger than the critical density, then the universe will contract. Oops. Why is that? Because gravity is going to pull everything together pretty much, okay? But if the density is less than the critical density, it will keep expanding forever. And this will be the consequence of not having enough material to exert enough gravity on all these stars and planets in the universe to keep them together. So they will keep expanding outwards forever. Okay. Now let's go talk about another weird concept related to the age of the universe and such, called dark matter. Okay. dark matter. So this was something discovered by Vera Rubin, another astronomer from back in the day. So Vera Rubin measured the velocity of distant stars as they rotate around the galactic core. Okay, so she found, surprisingly, that their speed is constant and also independent from and actually if the speed is constant, then it's independent from their distance from the core. Okay, this is the implication. So pretty much if this is the galactic core and this is some stars far away from the galactic core, she found that if this is V1, say, this is also V1, which doesn't make any sense, okay? Let's go see what happens in our solar system. So in our solar system, V drops for planets as we move away from the sun. In other words, the Earth moves slower than Venus, and Venus is slower than Mercury, and then Neptune is slower than the Earth, and so on. So if this is the sun, okay, and this is a planet that orbits the sun, the V of the planet is tangent to this orbit, right? So I went online and collected all these speeds, so I'm gonna plot them for you here. So on the vertical axis, let's plot the orbital velocity in kilometers per second, which is the form of the data I had in my disposal, and this is the distance in kilometers. Okay, I'm not gonna provide that, but okay, we have 0, 10, okay, this is 50, 40, 30, 20, and just pretend that that's 10, okay? So up here, with a speed of about 50 kilometers per second is Mercury. At about the speed of 35 is, and also it's a little bit farther away, right? So that's Venus. Then you have the Earth which is further out, and it has a speed of about 30 kilometers per second. Then you have Mars down here. And I'm not gonna plot everyone, so let's do this, okay? So things look like this, okay, in our solar system. So the further out the planet is, the slower it moves, pretty much. But Vera Rubin found this. But for stars in galaxies, the plot looks like this. This is the velocity, the distance from the center. So she found something like this. So this is a constant. V is constant, which was a crazy finding, okay? Now, how do we make sense of this? So the current explanation for this behavior, the current accepted explanation is that there exists, oops, I don't know how this happened, is that there exists a form of matter in galaxies that does not emit electromagnetic radiation, therefore we cannot detect it, okay? That does not emit electromagnetic radiation, which provides, so this form of matter provides the necessary GP, gravitational potential energy, for stars to move faster, okay? Because it doesn't emit electromagnetic radiation, it's called dark matter, okay? So this implies that there is probably more matter than we see, hence more density, okay? So if dark matter exists, then the density is higher than the one we measure from known matter, okay, the one we mentioned earlier. However, the problem is, at least at the point when this video was recorded, no dark matter has ever been detected. Okay, and let's close this video with two more concepts. The first one is dark energy. Okay, this is an even more mysterious, let's call it substance, if it can be called that way, in the universe. So we know that the universe is expanding. We do not know why it's expanding, okay? So we do not know. Hence, we do not know why. Hence, we devised a form of energy called the dark energy to explain why it's expanding. Nobody knows what it is. However, it is believed. Actually, let's make a new bullet point. So it is believed that the composition of the universe is as follows. So 60, actually, what did I do here? Sorry. So it is believed that the actual matter is just 5%, okay? 5% visible matter. the one you guys are familiar with. Then let's use blue. 27% is dark matter. And then whatever is left, 68% is dark energy. Okay, which is crazy, but this is the current accepted idea. Okay, so for those of you who want to go study physics or astronomy, this is an open question. The same goes for dark matter. Okay, so this is an active research field. People and researchers around the world are trying to understand what dark matter might be, how you might be able to search for it, and so on and so forth. Now, the last thing I want to mention is gravitational lensing. Which is a phenomenon observed because massive objects bend space-time. So what even is space-time? I'm not going to get into the details of this because it's a hypothetical construct that has real effects in what we observe in the universe. So think of a stretched paper, for example, which is flat, right? If a mass is placed on the paper, it will bend, right? So it turns out that this is the effect that any mass has on space-time. The more massive the object, the more this bending is. So what I'm trying to say is that if this is the space-time, which is flat, okay, if we put the Earth on it, so if this is the Earth, okay, so this is the Earth, it bends the space-time, okay, so that's the space-time, which is flat with no mass. It bends a little bit. If we put the Earth on it, it bends even more if we put the Sun on the space-time. So the Sun bends the space-time more than the Earth. And then if we go to something extreme like a black hole, right, a massive black hole, maybe this black hole, I don't know, has 100 times the mass of the Sun, then this is the black hole, okay, because the point, right? So this is the black hole. So it bends the space-time by a lot, all right? Again, we don't really observe space-time, but we observe the effects masses thrown in that space-time have in light rays, for example, okay? Because you can imagine that light will travel in a straight line, right? On a flat space-time, but if the space-time is bent, then because light travels in space, right, the light will bend, and it will bend even more when we have dealing with the Sun. In the case of a black hole, actually, we don't even have bending, so the light kind of stays inside the black hole, right? Nothing escapes the gravitational pull of a black hole. And let's go see this picture by NASA, actually. Okay, there is no better source, I guess. So let me read for you a little bit. So British astronomers Arthur Stanley Eddington, Frank Watson Dyson, and Andrew Crommelin proved Einstein's theory in 1919 with an experiment that centered around observing a total solar eclipse to see if the sun's gravity would bend starlight passing near the sun during the darkest part of the eclipse. So if Einstein's theory about objects bending space-time was correct, then you would expect to get light bending from stars that are behind the sun during a solar eclipse. Why a solar eclipse? Because that's the only way you can see stars behind the sun. Otherwise, the light is so bright that you cannot see anything, right? So what do they say here? 2 expeditions, one to the West African island of Principe, the other to the Brazilian city of Sobral, used a total of 3 telescopes, 2 in Sobral and 1 in Principe, to photograph stars near the sun during the total solar eclipse. So, as you can see here in the picture, the apparent position is in the straight line between the star, between where the star appears to be and the focus, right, your telescope. And there are 2 apparent positions for the same star, right, because the star is actually a little bit behind and the light that comes from that star bends because of the gravitational field of the sun. Okay, so this actually proved Einstein's theory. Why do we care about that? Okay, why do we care about gravitational lensing? Because studying light bending might help us find dark matter. Why? Because if dark matter exists, it will also bend. Okay, so let's use a mysterious color for dark matter. Let's use this violet here. So maybe this is dark matter, right? So if you observe the light from a star and you see that star appearing in 2 different positions, coming from 2 different positions, then you will know that the actual position of the star is in between those 2 positions. And the reason why you see it appearing, you see the same star appearing in 2 locations, is because of the presence of dark matter. Okay, and how would you know it's dark matter? Because nothing is there, right? So that's the idea. And this is the end of the videos related to Unit 5, guys, okay? I don't know if I will discuss Unit 6 yet. I'm trying to decide. Also, there is Unit 1, 2, and 3 that I haven't covered yet. And also, I'm gonna upload a new video saying what I want to do with this channel, which is to keep talking about stuff that I find interesting in tutorial styles, okay? So I will actually talk about machine learning at some point, undergraduate physics, even research level physics if I find the time, and the energy, okay? I hope you guys enjoyed these videos. Like and subscribe and let me know what you think about them in the comments, okay? Bye.